using kinetic theory-based approach is the computational cost, because this is F is a distribution function, which it's a function of molecular velocity. So molecular velocity is a three-dimensional. So you have to discretize in the velocity space in addition to physical space and time domain. So computation is very, very expensive. But at least this can give you proper kind of consideration of the rarefaction effect. This, we have developed a sort of this kind of gas kinetic solver, which enable us to direct solving the gas flow within the, using the digital image of the rock samples. This is an example to the Barrelstone kind of sample. You can see we can predict the mass flow rate against applied at a different Newton number. You can predict the flow property. So we can apply to this rock samples to see. I don't know. This video probably doesn't work. So there's this is a kind of more expensive approach, but it can provide us useful information in the future to help us to build a more kind of simplified engineering type of model to predict flow properties. But in shale gas, the difficulty is really come from this very dense gas can be in a supercritical state. So how can we properly consider this effect in flow behavior? This is a very simple kind of study in a dense gas flow through a simple channel. Yeah, we resolve the so-called Anscock equation, which is an extension of the bottom equation, so it can apply for dense gas. But it's very computationally extremely expensive, so we can only afford to do the simple channel flow. This red line is this mass flow rate against Newton number again. So red line is a Boltzmann solution. It's a full nonlinear Boltzmann solution. Yeah, this is the Anscock solution. You consider the different the L over sigma is the depth of the channel against the molecular size. Yeah, so this is basically the depth is similar to the molecules. So this is so-called confinement effect. You can see when the channel become wider compared to the molecular size, this solution is become closer to Boltzmann solution. But when channel become narrower, smaller, so the mass flow rate can be very, very different from Boltzmann solution, which means dense gas effect is a kind of can be dominant effect in fluid dynamical behavior at the pore scale. So the current challenge is how can we develop a computationally affordable dense gas model for us to calculate sort of permeability of the samples. But qualitative understanding of this kind of flow behavior already is very useful, because when we read the literature, so there's a lot of kind of when you try to measure shale rock permeability, there's a lot of kind of difference of different laboratory give very, very orders different kind of results. One reason we think the theory they use to extract the data might be really not right. So this commonly used pressure decay, this kind of method to measure the permeability. What they usually try to apply high pressure, so you can exclude the rarefaction effect, because fluid can be very dense, and apply a small pressure difference, so you can safely apply the Darcy law. Then you use the Darcy law to extract the information. But actually, it's not right. Like, because one thing is this is dense gas, yeah, can be. this confinement effect, this indicate confinement effect have all can affect the mass rate dramatically. So that's why if you do apply a kind of Darcy law type of theory to check the data, you will give you very kind of wrong results. So also we are now working on how can we use like molecular dynamics, this kind of data to plug into gas kinetic solver, which can provide us to proper boundary condition. Yeah. So we apply kind of mean field theory to model the attraction force between the surface molecule and the gas molecules, and apply like hard sphere, this kind of model for repulsive force. So that's we can predict the density variation, momentum, surface diffusion at the surface. So that's what we have been doing now. Finally, my conclusion is to try to develop kind of proper flow models. We need to resort to like a gas kinetic theory to have a bottom-up this kind of approach. And at the moment, we need to develop a proper dynamic boundary condition for gas kinetic model. And the dense gas kind of model, simplified the dense gas type of model, simplified the Anscock type model, we need really help from experimentalists for us to validate. This is extremely difficult, I found. Yeah. Finally, I would like to thank my cooperators. Thank you.
Thanks very much. You mentioned in your summary slide at the end that the confinement affects the permeability significantly. So what do you mean by that? And are you saying that the confinement is changing the shape of the pore space, or the confinement is impacting the size of the Knudsen layer which you're dealing with?
What I mean confinement, I do not kind of refer to the compressibility of the pore structure. I do not consider that. Confinement is usually in a gas kind of flow model, fluid bulk flow, you don't feel the molecules. Yeah? So molecule size compared to the flow passage is too small. So you neglect volume of fluid, yeah, of fluid molecules. Now confinement effect when in the nano kind of pore, yeah, like a methane molecule size is about 0.4 nanometer size, yeah. So in the kind of pore space, you have a diameter of 1 nanometer or 5 nanometer. So the size is not that small compared to the pore space. So that will lead to like a dramatic change of the viscosity or this kind of flow properties.
So the confinement is the geometry?
Geometry confinement, yeah. To, yeah.
It's very interesting to see how even at very low Knudsen numbers, there's still a very strong effect of slip. That was down channel flow. Do you think that effect is going to increase as you go to these small opening, closing pores with many interconnects?
Oh, it's a good question, because what I show is the simple straight channel, yeah. But problem is not that straightforward. We checked even with a kind of flow band, yeah. As a simple channel, you have one band or double band. The mass flow rate can be increasing or decreasing at different Knudsen number. So we haven't done the flow contraction expansion, where what will different will lead to. But one, I would say, want to be very simple, it will be increasing or decreasing. Should be flow related, like Newton number dependent.
Okay, thank you very much.
Okay, thanks.
Next suggestion. Last two, we're talking about noble gases in eggshells. Suggestion is working with me at the University of
Good morning, everybody. I'm going to talk about noble gases and gas shells, indicators of fluid movement. And this was a project that was supported by BG Group. It started in 2013, and now it's being supported by Shell, and it's going to continue up to 2019 June. And the experiments were done in Open University with Dr. Wachowski. And we've been greatly benefited by being a part of this Shell Gas Hub, which included Manchester University Imperial College, and feedback from our industrial collaborators. So I'm going to talk about the core locations, briefly talk about the methodology, which was developed in the course of the project, and the results. For the noble gases, I'm going to concentrate on the noble gases, but we've also analyzed it simultaneously for carbon and nitrogen. And discussion pertaining to the noble gases, because they're going to tell us about how well the fluids have been retained or lost from these samples. So this is what it looked like at the time when the shells were deposited. It was during the Jurassic period when the Gulf of Mexico was actually opening up. So it actually gave a very good conditions of restricted ocean circulations, which means organic matter was preserved. And there is potential of having shells with natural gas in them. These are my core locations, core 1, core 2, and core 3. And this is the color connotations I'm going to use throughout the talk. So for the core 1, it's going to be blue symbols, and core 2 is a pink one, and the core 3 is going to be reddish. It looks slightly different there, but it's how it's going to work. And they're from the Hennesville-Bossier Formation in US. So why noble gases? Noble gases are very interesting and very important because they are chemically inert, which means that we are going to get a lot of information related to physical processes like diffusion, like adsorption, solubility-related processes, using them. And the other advantage is that methane, if you look at this table that I put in there, in terms of dimensions, solubility coefficient, diffusion coefficient, is very comparable to the noble gases. So we have a range of noble gases starting from helium, neon, argon, krypton, and xenon that show a systematic variation in their sizes and systematic variation in their solubility and diffusion coefficient. So it gives us a very good tool. It's very handy if we want to look at the processes that led to any kind of fluid losses from the shells. And noble gases have other advantages. For example, we can divide them into primordial and radiogenic. So what happens is that there are some primordial noble gases, which means they are not produced subsequently after their incorporation, unless and until they're driven in by fluids or driven out by some other kind of movements. And then you have the radiogenic noble gases, for example, the 4-helium and the 40-argon, which can be produced over time from the decay of parent elements. For example, helium is produced from uranium, thorium, and argon, 40-argon, is produced from potassium. Advantage is that if you can measure the parent elements, which is what I've done in my study, so you have a definite ratio of 4-helium to 40-argon in the sample. So any deviation from that means that the system has been open to circulating fluids, loss of fluids, or even gain of fluids. So going to that, this is what my samples actually looked like. And from there, we recovered actually very tiny amounts of samples, like we analyzed from 2 to 8 milligram, 2 to 10 milligrams. A tiny amount of sample is required for this kind of work. And what we did is that instead of analyzing the bulk shells, we analyzed them by stepwise combustion, which means we heated them in incremental steps from starting from 200 degree to 1400 degree. By the time we reached 1400 degree, all the gases from the samples were lost. So which means we were sure that we have liberated all that was there. And if you look at this graphs, this is the fractional release versus temperature. And I've used different symbols for helium, neon, argon. I'm not showing the xenon results here. And I've compared it with carbon and nitrogen, the gray ones. And what's the advantage of doing that? The advantage lies in the fact that the carbon peaks when the carbonates decompose. The nitrogen peaks when the nitrogen decomposes. So when you liberate the gases with them, so you know that they are likely to be associated with clays. They're likely to be associated with other mineral components like carbonates. So that's an interesting part. And other thing for stepwise combustion heating, which we have used previously for other samples like diamonds, which we've done as a group with Adrian and Wachowski earlier, and we just transferred the technology, is that if they are sited in different sites, for example, adsorbed gases will be released at different temperatures compared to the gases that are sitting well within the pore spaces. I just wanted to show the two cores just to say that our methodology was very well established because we could reproduce results for different samples from the same core as well as the different cores. So we saw a systematic pattern in the release of the different gases. For example, helium roughly came out along with the clays at about 400 degrees centigrade. Xenon was adsorbed. I didn't show here, but they came around 200 degrees, so most of the xenon was adsorbed. So they were reproducible between the two cores as well as the samples within the same cores. We had done preliminary characterization before we moved into noble gases to see any differences that could be related to the noble gas pattern. And the core one was essentially mudstone. It had a lot of clay minerals. And I'm not going to go into the details, but the more broad difference between core 1 and core 2 is core 2 was coarser particles with a lot of detrital quartz. And the core 1 had a lot of clay minerals in them. And some of the noble gas results that I'm just going to show you could be related to that. And noble gas concentration. So you see the helium, neon, argon, and argon, the two isotopes of argon are shown here, 36 argon and 40 argon star. Note the asterisk. The asterisk means I'm only talking about the radiogenic argon here because argon can have atmospheric, which is not what I'm concerned about. I'm more concerned about the one that has been derived in the sample from the decay of the parent element, that's potassium. And the blue is the core 1, pink is the core 2. Why did I emphasize on looking at the gases? Because something that we are very concerned about is when the cores come to the surface, are we looking at superficial equilibration? So please look at the variable content, variable gas content. So we did see a lot of variation. The other thing to note is that there is no depth correlation. So we can say that it is not really what we see at the noble gas signatures are not related to burial diagenesis. We are definitely saying much more than that. And this is about the noble gas enrichment factor. So what does enrichment factor means? Which means we have used the different isotopes of noble gases, for example, 4 helium or 20 neon. We have normalized it to 36 argon for the sample, and then we normalized it to air over here. And you notice the V pattern in both the graphs. The colored symbols are for my samples. The gray ones are from literature study. So that is what you would expect, the gray trend, like a systematic trend like this, because that's how noble gases vary in terms of dimensions and atomic masses. So what does the V-shaped signals actually mean? It actually means that the samples have been exposed to circulating fluids. What happens is because neon can diffuse in preferentially to other noble gases. So if you see a circulating fluid that has influxed the shells, you will see a neon enrichment. Again, if you lose gases from the shell system, so all the noble gases will diffuse out, but xenon can stay behind preferentially because of its higher adsorption coefficient. So all the V-shaped enrichment pattern from my shells definitely indicates they have seen movement of fluids in and out of the shells. And here is my helium-argon results. I like to call them the here indicator. And what we find here is I have plotted 4 helium and 40 argon and 4 by 40 argon star ratio for all the 3 cores, the core 1, core 2, and the core 3. Because we know how much 4 helium can be present from uranium thorium measurements. We know how much 40 argon should be present from the potassium measurements. So the expected trends are given in your dashed line in all the cases. Please note that we have lost helium from the system. So the dotted ones, as against the dashed ones, the dotted ones are what we have measured. Look at the gap. So that means we have lost helium from the system for core 1 and 2. As far as the argon is concerned, it's quite well preserved. But if we go to core 3, we see an argon loss. So core 3 has seen higher temperature. If you have to lose this argon, which mostly sits in the clays, I'm not going into why it sits in the clay, but that's where it sits, which means it has been exposed to high temperature, like 200 degrees centigrade, in terms of, and we also do not find much noble gases in them, so most of the volatiles have been lost from the system, so maybe not very good from the economic perspective to look for natural gas farther on. So where are the noble gases sitting? So we are not going to talk about core 3. We have seen that core 3 has lost helium as well as argon, which means it has seen higher temperature. But if you look at the first 2 cores, the important thing is where are the noble gases sitting? So this is about 20 neon and 36 argon. I've normalized them to nitrogen. We have also measured nitrogen with them. And this is your 4 helium by nitrogen. So if we look at the sites, so this is where most of the samples come from, are associated with helium. Look at the linear trend here. So this means the 20 neon there on this linear trend and the 36 argon on this linear trend are associated with 4 helium. Now, most of the 4 helium comes from uranium thorium. And uranium thorium are enriched in organic matter. Many a times that organic matter is associated with clay minerals. So that is where most of the 20 neon, a part of the 20 neon and 36 argon are associated with the 4 helium. So they must be sitting somewhere in the pore spaces that are related to the organic matter and the clay minerals. But in addition, notice the 20 neon excess and the 36 argon excess. So there are multiple sites other than the organic matter and the clay minerals which are hosting these other noble gases like the 20 neon and the 36 argon. As far as the 36 argon and the 20 neon are concerned, they show very good correlation, so they go hand in hand. But helium seems to have a special site as well, where it sits. So we're talking about multiple sites, which obviously relates well with the previous talks. We've seen the multiple pore spaces, the pore dimensions, and the orientation. So we see the different citation, and I'm just going to show you how the retention is affected as to the sites where they are hosted. So if we look at this one, which is 20 neon and 36 argon as against 20 by 36 elemental ratio. So this is the advantage with the noble gases is that if it is not fractionated, if it is completely retained, we have very well-constrained air ratio and air-saturated water. Consider the air-saturated water as a water ratio. So this is where samples should be sitting ideally on these lines. So that is the elemental ratio. But that's not what we observe for our samples. It's definitely fractionated. Fractionated means they have deviated from the initial composition. So what has actually happened, we'll see it in a minute. So definitely the fluids have been lost or fluids have been intruding into the system. And in comparison to core 1, if you look at core 2, some of the samples do sit near the expected trend. So core 2 is better in terms of retention as compared to core 1. Core 3 we ruled out right at the beginning. And if we compare core 1 and core 2 stands at a better position. Remember that this was a sample that had a lot of mineral, that was less in the clay minerals, lower in terms of clay minerals, and it was more rich in detrital components like quartz, etc. So maybe the clay minerals and organic matter pore spaces forms a better pathway for liberating or losing gases as well. So while they can be hosting sites, they can also form pathways by which you can lose the gases. So I did some modeling to look into, for the first core, where we definitely saw a lot of gas loss. I'm not going to go into the details of the modeling, but I just wanted to look into processes such as diffusion and solubility from temperatures from 40 degree to 120 degree to identify what fits in best in terms of the gas I see. And what I find works well is that there was an enrichment. So there was an influx of fluid, and then after that, it we lost gases by solubility controlled processes. So at about a temperature of 40 degrees centigrade. So there was an enrichment. So there was fluids that was driven in, if you remember the neon enrichment V-shaped curve. And after that, there were fluids that was moved out, pushed out of the system. So there has been the cores have seen a lot of loss of gases. So obviously this has implication and economic implications if you're going to look for natural gas in them. And I also wanted to point out, contrary to what you see for neon and argon, where we saw trends of gas losses for 4 helium by 40 argon, for all the cores, they actually form a tight cluster. So there are some sites still that are very retentive. So we saw multiple kind of pore spaces in Professor Taylor's talk, and we do see from our noble gases, there are some sites from which we are losing gases, and there are some sites that are retaining gases. So I think the next stage is to relate which sites are better. And the next thing, the obvious question is, if for the shale gas community, that if you're losing gases, my study shows that for these cores, we are losing gases to different degrees, and we are seeing some of them are better in terms of retention. So we wouldn't have cared if all these processes occurred before the organic matter degradation. So the timing of this fluid loss is also very, very important. So, sorry. So here is a 3D plot between 20 neon normalized to nitrogen and the isotopic del 15N composition. I fitted in the best fit plane through my data, and this is the equation. Without going into the details of the equation, I can say that this is my initial 20 by 36 elemental composition. This is very close. This is what you would expect for air-saturated water. And this is for the nitrogen, minus 12. So if minus 12 is the initial nitrogen isotopic composition of the organic matter, it indicates that organic matter has already been degraded. So we are talking about all the fluids movement, the flushing out of the fluids post-organic matter degradation. So it has important implications as to the loss of shale gas that would be sitting in the shells. And I think just for summary, we looked into the V-shaped noble gas pattern, which suggested that the shells have been exposed to circulating fluids and they have lost gases from them as well. And in core 3, based on the 4 helium and 40 argon ratio, which deviated from expected 4 helium as well as 40 argon, we suggest that they've been exposed to very high temperatures. So the gases, there won't be appropriate samples to look for shale gas. And we saw that the loss of 20 neon can be related in the core 1 to solubility-controlled processes at temperatures of 40 degrees centigrade, and they were mostly occurring through clay and organic matter. And we did see that there are some 4 helium that was unassociated with 20 neon and 36 argon. They did not show the similar trends that were shown by neon and argon. So there might be some volatile sites, by which I mean pore spaces that are more retentive as compared to the other, although they are as well associated with clay and or organic matter. And so, yes, some pore spaces are definitely more retentive than the others. So I can say that we have developed a strategy that is, and the strategy is transferable. We've used it for American shells, but we've started using it for the European shells as well, because we can talk about cores that are good in terms of retaining gases and those which are not. And as far as the resources are concerned, that's over here in all in Europe. So this methodology is very much transferable and can be used for the study of European shells, which is what we are doing at the moment. So, yeah, that's it for the talk. Yeah.
David Byrne. For the, great talk, by the way. For the preferential helium-argon loss, do you think that's temperature controlled or just because of the recoil of helium-4?
Because I see it for argon, and and not, well, I see it for argon and not for helium, I would think that it's related to the temperature.
As you mentioned, David has a poster outside too, also about noble gases.
Thank you.
Thank you very much. Next, Bill Meredith from University College. We're going to talk about anisotropic fracture properties of shale.
Thanks, Adrian. Just grab some water. Tail end of a conservative cold. But hopefully won't be receiving my P45. Okay, well, thanks. Yes, indeed. Thanks for the invitation to come and present today. I want to talk about some work I've been doing over the last couple of years with, oops, I meant to do that one. With Nathaniel Forbes-Inskip, who's a PhD student at Royal Holloway College in London, and Mike Chandler, who was formerly a PhD student at UCL and is now a postdoc working in Manchester, still on shales. So before talking about the actual anisotropic properties of the shale, I wanted to say a few words about the stress anisotropy in the shallow crust. This is a simplified cartoon of what we think is happening, and generally the vertical lithostatic stress increases with depth faster than the horizontal stress, so that as we go to depth, we get an increasing stress anisotropy. And because fractures fractures are lazy, so they tend to fracture in the easiest direction, which is normal to the minimum stress, which means that we should expect to get always vertical fractures in the shallow crust. But we don't. What we see, this is a compilation published by Fisher and Warpinski a few years ago, where they compiled over 2,000 measurements from fracture orientations in US boreholes, and what they found was below depths of about 700 meters, the fractures were predominantly vertical as expected and predicted, but that at shallower depths, many of the fractures were predominantly horizontal, especially in sedimentary rocks and especially in shales, with this crossover, as I said before, around about 700 meters. So the question, one question is, why does that happen? And we suspect that that is due to the anisotropic nature of the material. So we've been investigating that by looking at some shale material which we collected from the Porth Kerry Formation at Nash Point in South Wales. The Nash Point shale, mineralogically and petrophysically, is extremely similar to the Eagle Ford shale from the US, but it's easier to get to, and we can get bulk samples. And it's part of an interbedded shale and limestone sequence of lower Jurassic age. And this is what it looks like in thin section. The microstructure is dominated by these shell fragments. So it's about 60% calcite, about 25% clay, with 15% quartz content. So that's the material, and you can see from its microstructure that it's very anisotropic. So we've measured that anisotropy by measuring the P-wave velocity as a function of angle from the bedding parallel direction. So this is the bedding parallel velocity and the bedding normal velocity, and you can see that it has a p-wave velocity of about 50%, velocity anisotropy of about 50%, and a Thomson anisotropy parameter of about 36%, and those values are extremely high, extremely high. So basically, we expect this elastic anisotropy, structural anisotropy to be reflected also in the rock's mechanical properties and its mechanical anisotropy. So we set up to measure that. And to define the anisotropy in a layered material, so what you have is essentially a planar fracture interacting with a planar material, and we can define, or people have defined, three principal crack orientations that are called divider, arrestor, and short transverse. And if we look at these in turn, the short transverse is where you've got a fracture that's growing in the bedding plane. So the fracture is parallel to bedding, and the propagation direction is parallel to bedding. So that's the equivalent of a horizontal fracture in the crust for a horizontally bedded material. The opposite is the arrestor geometry, where both the fracture orientation and the fracture propagation direction are normal to bedding. So that's the equivalent of a vertically propagating fracture in a horizontally bedded sequence in the crust. And the third direction is the so-called divider orientation, where the fracture plane is normal to bedding, but the fracture propagation direction is parallel to bedding. And I think that this will come out later, but an important point is that in the short transverse direction, the fracture is going along a single bedding plane, whereas both in the divider and the arrestor orientations, the fracture is sampling multiple planes of the material. So, since hydraulic fracturing to enhance recovery of gas involves propagating tensile fractures, we've measured tensile fracture properties, primarily the tensile fracture toughness, K1C, which characterizes the resistance to dynamic fracturing, and also we've measured the tensile strength. And so to quantify the anisotropy, we've measured those properties in these three principal directions, plus a range of intermediate angles to see how these properties vary with orientation. So this is the setup that we've used to measure the tensile fracture toughness. There are a number of recognized, approved techniques by the International Society for Rock Mechanics for measuring fracture toughness, and this is one of them, the so-called semicircular bend sample geometry, which we make by essentially taking a large diameter, 76 millimeter diameter core and cutting it in half. And we can make samples at different angles simply by cutting those discs at different angles to make cores at different orientations. And this is the setup that we use. We have an alignment block in the middle here, which keeps the span at the correct distance apart, and also a blade on that, which keeps the alignment and the centering of the sample, and then we simply load it in compression at a constant deformation rate. And if we do that, we get load displacement curves that look like this, where we're plotting load in kilonewtons against displacement in millimeters, and what we see is, unsurprisingly, that the short transverse, the bedding parallel orientation, we get it's the weakest. It fails at the lowest load, and the arrestor orientation is the strongest, and at intermediate angles we get intermediate failure loads. And if we do the calculation to calculate the fracture toughness of the material, plot that. Oh, sorry, before I get to that, just going to show some fractured samples, semicircular bend samples. Here's a short transverse sample. We see that the fracture is very straight because it's propagating along a bedding plane. If we look at samples failed in the divider orientation, so the bedding plane are in the plane of the screen here. So this is actually a bedding plane that we're looking at. We also get straight fractures, but the fractures growing across multi-layers simultaneously. And in the arrested direction, we usually get much more tortuous fractures because the fracture is growing across multiple layers, but sequentially rather than simultaneously. So these are always rather more tortuous as the crack finds its way across the layers. And if we plot that up, then we see that we get the weakest, lowest values of K1C in the short transverse direction, the bedding parallel direction, and the highest value in the arrestor direction. And the arrestor and divider orientations, we get very similar values, which I guess is not surprising because in both directions we're sampling multiple layers, except that one is simultaneously and the other is sequentially. And we get an anisotropy of about a factor of 3 between the strong direction and the weak direction. Excuse me. So we also measured the tensile strength as a function of orientation, and here we use the so-called Brazil disc technique. We take 40 millimeter diameter discs that are 20 millimeters in thickness, and we put them between 2 curved jaws, which we then compress together, and that compression produces a tensile stress at the center of the disc, and a fracture grows outwards from the center, and simply by putting the disc in at different angles, we can measure the tensile strength as a function of angle. And what we see is a very similar pattern of behavior. So here is a broken disc, and you can see the tensile fracture that's grown through the center. This is an arrestor orientation, although you can see that the bedding on this scale, the bedding is not exactly straight and parallel. So we get so at some points the fracture is growing at an angle to the bedding because that's the nature of the material. So here again we've measured it in the 3 principal directions, and every 15 degrees between the short transverse and the arrestor orientation. And again we see this general increase and an anisotropy of a factor of between 3 and 4 between the bedding normal directions and the bedding parallel directions. But the data is considerably more scattered and variable than the fracture toughness data, and that's because the fracture toughness is a more fundamental measure of fracture propagation than the tensile strength. We can discuss why that might be later. But a similar kind of activity. So if we can relate the tensile strength and the fracture toughness to each other, theoretically, just by considering the elastic modulus and a critical floor size, and I've plotted our data all come within this ellipse down here. I've plotted that on a plot superimposed on this plot from Zhang et al. 2002, where they compiled a whole set of tensile strength versus fracture toughness data for a whole range of rock types, which from data they obtained from the literature, and you get a sort of a quasi sort of linear trend. So I think this compilation and shows that the shales are obviously classified as weak rocks because they're right down at the bottom left-hand corner of this diagram, but both the Nash Point shale, the black circles and the black dots that we've measured using two different measurement techniques, and some previous work by Mike Chandler on Mancos shale from the US, all plot within this elliptical area here, and they all fit the general trend. There's very little data on shale, and the only previous study we could find where both things have been measured is some measurements on Anvil Point shale back in the 1970s, and that does not fit the trend, and we think that's because they used a rather dubious method for measuring fracture toughness, which is no longer considered an appropriate way to do that. So it doesn't fit the trend. It sits up here. The fracture toughnesses were too low. What are the implications of this for the hydrofracture orientations that are observed in the crust? So we now have some data which helps us to explain the observed orientations of hydrofractures in these US boreholes. And what we're suggesting is that the fracture toughness and strength anisotropy of the shale material dominates the orientation of fractures in the shallow crust. But as we go deeper, so we get horizontal cracks in the short transverse orientation in the very shallow crust, but as we go deeper, because the crustal stress anisotropy increases with depth, the crustal stress anisotropy dominates over the material property strength anisotropy once we get below a certain depth, and then we get vertical cracks in the arrestor orientation, and that crossover seems to occur at a depth of around 700 meters. What we're engaged in currently is making similar measurements, but under confining pressure at reservoir pressure conditions, and to see how that varies. And we think that's important because, of course, you don't want to generate horizontal fractures, because if you do, you're likely to encounter faults, and if you inject fluid into already highly stressed faults, then you can trigger seismicity on those faults, which is something that I guess nobody really wants to do. So in summary, we've seen that Nash Point shale is an exceptionally anisotropic material, both elastically and mechanically. The fracture toughness and tensile strength are 3 to 4 times higher in the arrestor and divider, i.e. bedding normal directions, than they are in the short transverse or bedding parallel orientation. The fracture toughness and strength values increase progressively at intermediate angles, which is important because often fractures are not growing in those principal directions. So fracture toughness and strength anisotropy dominates the orientation of fractures at shallow depths, whereas crustal stress anisotropy will dominate propagation at depth below 700 meters. And as I said, current work is focusing on measuring these properties under pressure and temperature conditions relevant to reservoir depths. I think that's it. Thank you very much.
Sorry, I know it was a rather fundamental sort of term you used, but I didn't fully get what you meant by fracture toughness. Is that like resistance to fracturing?
The fracture toughness is the resistance to dynamic fracture propagation. So okay. It comes from Griffith's fracture theory on the basis that fractures propagate from pre-existing flaws or defects in a material which produce a stress concentration at their crack tip. And one of the reasons you get a lot of scatter in tensile strength data is that the rock will contain pre-existing fractures and flaws of many different sizes, and depending on what flaw you've already got in your sample and its orientation, that will affect the tensile strength that you measure. So the concept of fracture mechanics and fracture toughness measurements is you put a notch in the sample and you put in a notch which is bigger than any natural flaw, but it's your notch and you've put it in, so you can then calculate how the fracture propagates from that known flaw size of a known orientation. So you get a more fundamental understanding of the resistance to fracture of the material.
Okay, I get it.
Sorry, that was a long answer to a short question.
Very well explained. Very well explained.
Thanks. Have you looked at fracture distribution in situations where the horizontal and vertical stress are quite similar?
So you're talking about an isotropic stress field. Well, I mean, that's essentially what we're doing here, because we're not applying any confining pressure.
Sorry, I meant in the context of right now you've got a crossover about 700 meters where the fractures which you're developing are becoming vertical from horizontal to vertical. Yeah. I would be expecting that if you have a more similar profile in terms of the vertical stress and the horizontal stress, that you would see the crossover at a much different depth.
Yes, I think that's exactly right. So I mean, I think when you look back, it's that this plot. You know, there's a lot of noise. There's a lot of noise on there. So the figure of 700 is a general average, but I imagine that if you mined this data in detail, then the reason for the scatter is because of these different stress depth profiles. I mean, because they're all different. The one I put on the cartoon at the beginning is a very simplistic view of that, but no, I think that's exactly right, yeah. And also, we would expect that to change with the material properties, because the actual strength anisotropy of the material will change at higher confining pressure as well. So I imagine that the depth at which that crossover occurs will be on any individual case, both the material and the local crustal stress conditions. Both of those will affect that. I agree, yeah.
One more.
You mentioned that you want to avoid horizontal fractures. Could you amplify why?
Well, I mean, I think, is this not what happened at the Priest Hall thing in Lancashire? If you generate a horizontal fracture and you intersect a pre-existing fault that's already highly stressed, you're pushing a high-pressure fluid into that fault zone, and you'll decrease the normal stress across the fault, and therefore you could induce the fault to move and rupture and produce an earthquake. And whereas the actual hydrofractures themselves can only produce tremors of very, very low magnitude, if you actually inject that fluid into a large fault that's already highly stressed, you could actually trigger seismicity of much higher magnitude, which would be a problem. And that's why you think you don't want horizontal fractures.
Thank you very much.
Thank you very much, Phil.
Okay, cheers.
Next, Jill Cooper,
And I
USA. Going to talk about
I believe you said you had a conservative cold. I'm going to stay liberally healthy. I used to work at a health department. It's like, if anyone wants to borrow one of these later when you're presenting.
over to you.
Thank you. Jill Cooper, I'm with Anadarko. Did anyone else from Anadarko make it? we'd sent out a request, we have a Uxbridge office, and I think many of them are over in Africa right now, so they couldn't join me. But I'm honored to be here. Thank you very much. I can tell you this is the most technical thing you're going to see, my entire presentation, so you guys can relax. You just had a very, very intense morning. But this, of course, is our cautionary principle that we have to say. Who is Anadarko? We're an upstream and midstream oil and gas company. I work in the Health, Safety, Environmental group. I do a lot of the stakeholder, investor relations, regulatory, work a lot with regulators, and in doing so, I work a lot with the technical teams within our company to understand what it is we do and be able to translate it into English and many other languages, as you can see. We are a global company. These are the countries we're operating in currently and our focus areas. Today, they asked me if I would talk about U.S. So while many of the practices I'm going to talk about we do across the world, it's really focused on our Colorado operations between Denver and Wyoming. So it's just in an urban interface. We are working in communities. They moved into our operations typically, but it doesn't matter. They're there and we work closely with them. So one of the things that we do is we meet and work with our communities and we talk to them about what we do. And what a lot of people don't realize is that the big drill operations that you see and the completions operations you see are only there for 3 to 10 days, right? A drill rig's 3 to 5 days, a completion rig is 5 days. The life of the facility looks like this. That's the 20 to 30 to 40-year picture of a gas operation. Oil operation isn't much different. You could have the derrick, the rig going up and down the pump jack. But you don't see the activity that you see in the 5 to 10 days, let's just say, of drilling and completion. That's the first thing that surprised most people. Now, why does that matter? Well, what we have done in the United States, and it is happening in other countries, but the US really, I think, kind of took off with this first, is we started changing how we do operations. Of course, fracturing has been done since the 30s, 40s. It's not just our industry, geothermal, mining, other industries do hydraulic fracturing. It's just fracturing with water. But the term and the scale, the term got a lot of attention in part because the scale of our operations started going up. Why? Well, we learned how to do horizontal drilling. We learned to go deeper. We learned to put more wells on one pad. I've seen up to a 52 well pad, 52 wells on a single pad. It was actually quite a beautiful thing because there were no separation tanks. It was 3-phase gathering. They shipped the oil, gas, and water to a centralized facility to separate it. So all you saw were 52 pipes coming out of the ground, and then the pipe disappeared underground and it went to a centralized facility. But what we've been able to do is we've centralized operations, 6 to 10 to 12 to 36, now 52 wells on a pad. We've shrunk the amount of surface footprint we need. The average site's 30% smaller, even though we have more wells because we have less equipment on the surface. We're getting 60 times more oil and gas and 10 times the amount of energy from a tenth of the wells. So this diagram down here, one of our federal agencies puts it together, just showing the surface footprint of shale versus conventional versus wind versus solar for the same amount of energy. We also talked to our communities about this is what we used to look like, 6 individual pads. Now we've centralized them, and you get down to the kick point, and that's where you start going out. So you go down 8,000 feet in a common location, and then you kick out from there. Why does that matter? Well, because we can reach a lot further underneath communities, cities, other operations like agriculture, without them ever knowing that we're there. We no longer have to go so close to where we're going to drill. We can drill down and then kick out. So it allows us to access a lot more resources without the impact. Obviously, it also allows us to go along the line where, as you've heard earlier, nature puts these things in slabs, and we're able to hit more of the sweet spot with the horizontal than we ever will with a bunch of wells going in the ground vertically. So in the United States, what we like to explain to people, and this happens to be a Denver building up here, but the Empire State Building is the one I had on the last one, it's very, very deep. And if you look here where our groundwater table is at, it's pretty shallow. Usually groundwater tables for human consumption are going to be less than 1,000 to 1,200 feet below the surface. And so we're drilling at 6 to 8, sometimes 10,000 feet. So we've got a lot of layers of rock in between. And the protective wellbore that you have in place through the groundwater and about 1,000 to 1,200 to 1,800 feet below it is a lot more protective than when you get down deeper, because you don't need that anymore. You're not as likely to lose anything. So one of the things that we explain to people is we're in the business of pulling oil and gas out of the ground. We don't want leaking wellbores. We can't afford to spend millions of dollars on a site, drill a hole in the ground, and then have the well not contain what it is we're pulling out of the ground. So we're highly motivated from a business perspective to have a really good wellbore. And wellbore protection is what we focus on. You heard about chemicals earlier today. We're all working with green chemicals and everything. The one area that we have a challenge finding something greener is corrosion inhibitors and scale inhibitors. Why do we use them? To protect the metal, protect the wellbore integrity. So if someone could figure out a better way to do corrosion inhibitors and scale inhibitors, that would be awesome, or biocides. Because the only reason we're using those things is to protect the metal from the stuff we're pulling out of the ground and the water we send down and then what we pull back up again. So most of what we're using, you heard less than 0.5% are additives. And we are using guar gum, and we're using a lot of things that people use in their homes. We try to use food product quality level things when we can, but sometimes we're using chemicals because we need to protect the wellbore. That's the primary use of these. A lot of attention in the US has come on our water. Now, they used to say we were a large consumer of water. In the state of Colorado, we are 0.08% of the state's water use. All oil and gas combined, it's 0.08% of the state's water use, for surface water or water use. Or I should say, water that can be used by the public for other purposes. That's not very much. One of my good friends works for an environmental group called Trout Unlimited. I can't get them interested in us because they're like, you guys are such a small user compared to the municipalities and agriculture and others. So what we started doing, though, is taking a look at our water world. And in our company, this is a diagram like 20 companies came up with together. We have a group that works together on technical issues. Our company used this internally once it was developed to really take a look at where do we have opportunities around water. So I call this the alien because literally, this looks like an alien that's going to roll off the map. But we use water throughout the life cycle of our operations, and then we get water back. So nature gives us oil, gas, and water, and then other things in the soils and metals and other things. To picture it, the water we pull out of the ground is formation water. We also call it produced water. You can also call it groundwater. It's just been sitting down there for millions of years with oil and gas. So it has BTEX, big surprise. It has total dissolved solids. It has heavy metals. It has a lot of other things in it that nature put down there because it's been sitting down there for millions of years with oil and gas. In addition, we put fresh water down or our own recycled water to fracture. What we found out is the hardest water to characterize is the surface water we use to fracture, because it has been impacted by everything at the surface that's being used. Other things, hydrocarbon depositions from surface, chemicals used, humans use, pharmaceuticals. It has a lot of stuff in it that we don't measure because we don't care about that being in the water when we're fracking. We care about certain things. We need the water to have a certain level of quality to frack, and thanks to our service companies, I know some of them are here today, we've been able to use more and more brackish water and less clean water for fracking, which is great because it doesn't take as much energy to clean it up, and we can save fresh water for other uses. The challenge we're running into is while some states and localities and businesses want our water, the produced water, it's easy to measure. It's easier for us to measure what nature put in there. It's a little harder to characterize what came in the surface water we use to frack with. That's kind of where we're stuck right now. So one of the things that we try to explain to people when we talk about water is part of what I just said. If you think about 40, 50 years ago, oil was king. What do we do with natural gas? We flared it because we didn't have midstream. What happened? Economies of scale. We learned how to set up midstream, capture natural gas, which was a waste at one point, pipe it into a centralized treatment, basically gas treatment facility, clean it up, and now utilities are using it for a pretty clean source of energy. Nature gives us water. At what point will the economics and the economies of scale be at the right point where we can treat that water and keep it at the surface? You guys are talking about it here. We're doing it in the United States. They're doing it in the Middle East, in Israel and other places. They need the water. It's water that for us, it tends to be inland, in the middle of the country more. Water's expensive to move. The cost that inhibits us from probably keeping more water at the surface is the cost of transporting and storing the water. It can be up to 60 to 80% of your water cost. Treatment can be expensive, but it's not the most expensive part of this. So in some areas, the treatment costs are down at 50 cents a barrel of water. That we measure things in barrel because we're oil and gas, we measure everything in barrels. But in addition to that, you're probably paying $1.50 to $3 for transport and disposal. So you can see it's really depends on how clean you need to treat your water but also how expensive is it to store and move water. Water isn't necessarily easy. Now, the oil and gas industry is in the business of moving fluids. We've done it for a very long time. Since we've been in business, we've been moving fluids. We are trying to get better at moving fluids. Water is just one more fluid that we move in addition to natural gas liquids and oil. So we started realizing we're actually pretty good at moving fluids and pipelines. So instead of trucking fresh water to our locations, why don't we see what it looks like to pipe it? Now, this is fresh water, not produced water. We use temporary lay-flat hoses. These are things we rent from a company. They roll up, they roll down, kind of like your backyard hose, except they're really big and they're flat. And we use them where we need to. So we set up this whole grid. This is in Colorado. The purple lines are actual, usually they're ditches, like farmers' ditches. We either enhance a current set of farmers' ditches or we built one. Someday we won't need them anymore, and some municipality or a farmer will probably get them from us. But that way the infrastructure isn't just for our purposes. It can be used long-term, more sustainable. It can be used by other entities in the long run. So we have that system, and when we need to drill over here, we'll put a lay-flat hose. So we're not building a permanent pipeline because we don't need it for that long. Pipelines aren't very popular these days in the United States. We can put a lay-flat hose on the ground, and when we're done, roll it back up, go to the next spot, use the same lay-flat hose. It's just fresh water, so if it spills, like if you get a pump a leak in your lay-flat hose, it's just fresh water. So it's not, the government has said it's okay, we don't have to report fresh water as a spill. It's Colorado, the rules are so stringent. If you pour a cup of coffee on the ground, technically it's a reportable spill. We don't report coffee spills, but technically the agency could make you do that. So we use these lay-flat hoses, and if you see some of the numbers we have on here, when you start talking to your community that you work within, they're not so concerned about your methane emissions. They're often not concerned about groundwater, because we've talked to them about that. It's the surface. Come back to the surface. We've talked a lot about underground. Now we're at the surface. They care about traffic, noise, lights, seismicity at the surface. They care about safety of their families. When we have thousands of trucks driving up and down the roads, we help them fix their roads, we work with the local communities, we invest in the infrastructure, but it's hard to ignore the fact that there's safety issues when you got a lot of water trucks driving up and down the road. We removed, now I think they're saying 1,500 trucks per day. At one point it was over 2,000 trucks per day in this one community by using lay-flat hoses. Kind of seems like a no-brainer after a while, but our water guys are really continue to be focused on how do we reduce our surface footprint. These are the companies that work together on technical issues in the United States. It's called the Energy Water Initiative. I happen to be the chair because I don't know anything, so they let me lead them. These guys are all technical like you guys, and I do not know what they know. So we pull them together we meet 4 times a year. In September, we met at our operations in Colorado, what I just showed you a map of, and we gave them a tour. We went to Noble as well. In November, December, we're going to go to Midland, Texas, and go to 4 other companies' sites, Chevron and some others, and take a look at their water treatment. So it's just a group that works together, moving technology, and I know they love to give their input and their opinions, so let us know if you have questions. When it comes to the costs, this is a pretty dramatic chart, and it is cost per foot of the well drilled, like we count the distance down of the well drill. If you look from 2013 to 2016, that's a pretty significant cost drop. That's one of the reasons the U.S. continues to make it economical to drill and produce in the United States compared to purchasing it from another country, is we're getting better at it. Every year we're getting better at it. And the cycle time means the number of days it takes to drill a well. It's going down significantly. We're getting a lot better, a lot faster, a lot safer at it. So hence, that's driving the economics down as well, and probably driving the Middle East a little crazy. But we're getting better at it. And so that's why we keep being able to hit the next market target. When the prices go up and down, we've still got a lot of operators that are still out there producing. The other chart I really like, because I'm an air attorney, is the air chart here. If you look at this, this is our actual volatile organic compound emissions at the surface, based on and compared to our productions and per barrel, and look at where the emissions are going. So of course, as we bring more wells on, right, we continue to add to our inventory of gas of product that we produced, and you would expect to see the air emission line go up, but it's dropping down. Why? Well, if you look over here, this is what we used to look like. This is what we look like today. If you centralize your operations, it's easier to control emissions because you're not trying to control 6 different sites or 4 different sites. You can put one set of controls on the whole thing, the vapor recovery units. But what we really did that I think is interesting, they call this Gen 3, Generation 3 sites. We're working on Gen 4 now, is we got rid of tanks. If you see here, these are the tanks. We got rid of tanks. We now, as you can see down here, are some of the details. We put pressurized vessels to replace the tanks. The tanks were controlled with a flare. But anytime you have a piece of equipment, there's a greater likelihood of leaks happening. Valves, flanges, thief hatches getting left open. You eliminate all those units, you've eliminated leak sources and your emissions. So we are getting really close. We can't say zero. The engineers will never let us say zero emissions, but we are getting really close to a near zero emission facility at the upstream side. We have, last count I had was 64 of these constructed in Colorado, but I'm sure they're well over that number now. I need to get an updated number. We've also hooked up to the grid where you can and use more electricity to run things. So we got rid of diesel sources on the location as well. I played around with all the transitions, every single one. I think I have every one of them in here that PowerPoint allows. So we have something called the Integrated Operations Center. If you come work for oil and gas these days, you're not necessarily getting in a truck and driving out to a site as much as you used to. Most of our men and women are sitting behind computer screens in these integration operations centers. Offshore has been doing this for a long time because what they need to see is 5,000 feet underground in the ocean. So they were always using computers. It's coming onshore, and it's really, really been beneficial. We are getting a lot more production. We're at lower costs. We're being able to identify issues a lot faster, a lot more remote technologies being used. Instead of sending somebody around to drive around and look for problems, we're sending somebody out because we identified a problem, and they usually have the right equipment and the right things, information that they need to fix the issue a lot faster. Drone technology is coming into fashion in the oil and gas industry. They've been using it for pipeline inspections for a long time. I know you guys may have limitations on the use of drones here. It is tremendous when it comes to determining methane leaks and safety issues and keeping people out of trucks until we know where the problem is and we can send them there with the right equipment. Safety is a big deal in our industry. The other thing that we'll talk to our communities about is where they actually see the benefit economically. So this number here, the 642 million, that's Olive Oil and Gas. Anadarko's, we're APC, Anadarko Petroleum Corporation. We're at 127 million. So this was in 2016. We paid in 2017, but it was for 2016 taxes and royalties and other things. This is what we directly brought to Weld County, one of the counties that we work in. This isn't all of Colorado, it's just the one county. It is the county we do the most work in. And you can see the kind of how the money gets divided up, and a lot of it is for the services and the schools. So why, the next step we took though, because in Colorado, it's a highly engaged, highly motivated populace. They live in Colorado mostly because they love the mountains, they love the outdoors. They don't want to see industries come in and compromise what they moved there to enjoy. So we started listening to our community members, and this is something the Shell Corporation came up with a couple years, or probably like 15 years ago. But this is the societal transition over time. You'll find this in mining, oil and gas, agriculture, you name it. Every industry out there is struggling with this right now and learning it. So in the 1960s, before most of you were born, it was trust me. They trusted the government, they trusted industry. And then in the 1970s, 80s, they started saying, well, you know, we need you to tell us more. So in the US, we started doing more reporting to the federal government. We had to start disclosing more things. In the 90s, sustainability came around, and it was show me presentations. I want to see what you're doing, I want to hear your stories. Today, we're in the engage me phase. So what it means is our community doesn't want to just hear what we do. They want their opinion heard, and they want us to have a dialogue with them and say, how can we address your concerns? Which is really, really good for a company like Anadarko because we're not afraid of it. Their expectations have increased, and we're responding, and we created a couple different programs. One, we use our website. You can go on there and read about what we do with induced seismicity. We have our own internal group. We've joined the Texas Center on Integrated Seismicity Research and Stanford's, it's called SCITS. The acronym escapes me, and Center on, I can't remember but it's Zobac's group over in Stanford. So we joined those two institutions because they're improving the data around seismicity and what we're doing and how we can continue to minimize the likelihood of induced seismicity from water disposal and from hydraulic fracturing. Only felt at the surface. We all know we're causing microseismic down 8,000 feet below the ground. Our concern is when it comes to the surface. We also put on our website a lot more about air quality. We worked with Environmental Defense Fund. They did a life cycle study on production, gathering, transmission, distribution, trucks.